Hello, welcome again. We are solving some questions of heat transfer. The topic is one dimensional conduction heat transfer. Question number 10 is consider steady state conduction across the thickness in a plain composite wall as shown in the figure, exposed to convection condition on both sides. So this is for one side, this is the other side, this is hi t infinity I, this is 1, this is 2, this is h naught t infinity naught, and this is L1, this is L2. So given that H1 is equal to 20 watt per meter square per degree Kelvin, H naught is equal to 50 watt per meter square per degree Kelvin, T infinity I is equal to 20 degrees Celsius, T infinity O is minus 2 degrees Celsius, K1 is K1 is 20 watt per meter per degree Kelvin, K2 is 50 watt per meter per degree Kelvin, L1 is zero point 0.3 meter and L2 is 0.15 meter. Assuming negligible contact resistance between the wall surfaces, the interface temperature T in degrees Celsius of two walls will be option A minus zero point 0.5, option B 2.75, option C 3.75, option D 4.5. So this is the case here. This is Hi is convective heat transfer coefficient, T infinity I is your temperature on one side, and T H naught is convective heat transfer coefficient, and T infinity or is also your temperature on other side. This is L1, this is L2, this is K1, this is having K2. So these atmosphere offer resistance, that is RT1, and this also offer resistance, that is RT2. This offer resistance, that is RT3, and this is RT4. So these resistances are in parallel, so equivalent resistance will be summation of these. And here the temperature T infinity I, and here the temperature T infinity naught. So heat flow will be T infinity I minus T infinity naught divided by summation of four resistance. Okay. So now this is the heat flow, and the heat flow can also be given by this T infinity I minus T inter divided by resistance up to that RT1 by RT1 plus RT2. Okay. When we take this temperature and this temperature, so we will take these two resistances, because same heat is flowing through this wall and going to this and going to this. Okay. So here the resistance per unit are so here the different values are given. The value of H is given, so that is if we take area as 1, then it will be 1 by 20, RT1 will be 1 by 20, and RT2 will be your L1 by K. So L1 is L1 is 0.3 by 20, and L2 is 0.15 by 20, and your this is your 1 by H infinity, so 1 by 50. So these are the four resistances. Okay. And T infinity I and T infinity O is also given. So that is minus 2 and that is 20. So total heat transfer will be 20 plus 2 divided by summation of these four resistances. And in this equation we can put T infinity and put RT1 and RT2. Okay. So equating these two, we can find out T inter, that is 3.75 degrees Celsius. So answer to question number 10 is option C. Next, a 30 centimeter thick wall of 5 meter into 3 meter size is made of red brick. K is equal to 0.3 watt per meter per degree. It is covered on both sides by a layer of plaster. A 2 centimeter thick. K is equal to 0.6 watt per meter per degree, and the wall has a window size of 1 meter into 2 meter. The window door is made of 12 mm thick glass. K is equal to 1.2 watt per meter per degree. If the inner and outer temperature are 15 degrees Celsius and 40 degrees Celsius, then rate of heat flow through wall is option A 5.3 kilowatt, option B 3.3 kilowatt option C, 2.5 kilowatt option D, 7.8 kilowatt. So this is the schematic diagram. This is the outer side, and in between there is a window, and this is the inner side. Okay, and here the temperature is 15 degrees Celsius, and here temperature is 40 degrees Celsius. Thickness of this plaster is 2 centimeter, and thickness of this plaster is 2 centimeter, and this is your 30 centimeter. 30 centimeter brick wall. Okay. So now we can assume that this this portion, or this portion is in parallel with the window. Okay. So distance of this is RP1. This shaded portion is RP1 up to this hole. Okay. RP1, and distance of this is RP2, and distance of brick wall is RP. Sorry, distance of this is RB, brick wall, and distance of window is your temperature T1 at the temperature T2. Okay, so RP1 is equal to RP2 is equal to delta by K. RP1 is equal to RP2 is equal to delta by K. Okay, and here delta is the thickness of this is 2 centimeter or 0.02, and K is 0.6. Conductivity of this is 0.6. 0.6, and conductivity of and area of this portion is, because the total area of the wall is 5 into 3, and we will subtract the area of window, so that will be the area 5 by into 3 minus 1 into 2. Area of window is 1 by 2, 1 into 2. Okay, so that is the distance of that is distance, this distance, and as this material is same, so this distance. Okay, so that is RP1 and RP2, and distance of brick wall is, again this is 0.3, thickness is 0.3 meter, and divided by K 0.3, and this is your 5 into 3 minus 1 by 1 into 2. Okay, so that is a brick wall, so that is 76.92 minus 3 degrees Celsius per watt. So this is the distance of this portion, and this is the distance of this portion, glass wall. Okay, so these are the two resistors that are in series, and these are the three resistors actually which are in series. Now this resistance of glass is also in parallel. So first of all we find out the total equivalent resistance of this wall. So that will be RP1 plus RB plus RP2. So that will be that we have calculated 2.564 into minus 3, and this is your RB is 76.92 into minus 3, and this is also same. So equivalent resistance of this branch is 82.048 and minus 3 Celsius per degree watt, and the distance of window glass is the thickness of window glass is 0.02, 12 centimeter. Okay, and area is 2 into 1, and conductivity is 1.2, so that will be 5 into 10 to minus 3. So now equivalent resistance can be calculated by using the formula 1 by RT, 1 by RE plus 1 by RB. So that value comes out as this value. Okay, and this is your 4.713. So now T1 and T2 are known, that is 14, 15. So we can put the value of RT on this. So the heat transfer will be 5.3 kilowatt. So answer is option A. Okay.